9.4 is titled Permutations and Combinations. And what 9.4 does is it talks about the number of ways that certain things can happen. Okay, so it's kind of counting techniques or counting processes. To get started, the first bit of information may or may not be something familiar with you. If you've seen an exclamation point, mathematically speaking, called a factorial, just let me know. Just raise your hand real quick. A few of you have. Okay, so it does not mean the N is excited or yelling or angry. It's not any of those. Okay, this actually has a mathematical notation, connotation, or a meaning behind it. And what it means is that you take the number n, whatever that number is, and you multiply it by the value 1 less, and then the 1 less than that, and you work your way all the way down until you multiply by 3, and then 2, and then 1. So all the natural numbers get multiplied out lower than that value. So I'll come back to the 0 factorial in a minute, but 4 factorial, it means that we're going to multiply out 4 times 3 times 2 times 1. That's what that notation means. So what is 4 times 3 times 2 times 1? 24. Yeah, it's 24. Absolutely. Okay, so that works for all natural numbers. That's why they're using the letter N here, is to stand for natural numbers, which are counting numbers 1, 2, 3, 4, and so forth. The value 0 factorial actually has a defined meaning as well. It is defined to be the number 1. And you'll see when we start working with problems why we need it to be the number 1 to make it make sense, but I'm not going to offer a proof for why it has to be. Okay, we're just going to take it as a defined thing. 0 factorial is equal to 1. Back in number theory, we encounter what's called the fundamental principle of counting in chapter 2. And it says something like this. If event M can occur in M ways and event N can occur in N ways, then event M followed by event N can occur in Mn ways. Okay, and a real quick example of that is Pizza Planet, which is from Toy Story. Pizza Planet offers 3 kinds of salad, 15 kinds of pizza, and 4 desserts. How many different meals consist of 1 salad, 1 pizza, 1 dessert? Okay, you've seen these kind of deals like before, like Chili's does this, right? Like you get an appetizer, an entree, and a dessert, or a drink, or whatever. Like they do this. So this happens quite frequently. So what we actually do is there's 3 things you're choosing from. So I'm just going to make 3 spaces like placeholders. So the first thing you're choosing from is how many different options you have for salad. And how many do you have for that one? 3. And how many options do you have for pizza? 15. And how many options do you have for your dessert? 4. And what the fundamental principle of counting says is that if you multiply those outcome values together, that will give you the total number of ways that anything could have happened to give you a different kind of meal. In some way, shape, or form, it was different than somebody else's. So 15 times 3 times 4, what do you get? 180. There are 180 different meals. We had a scenario like this happen actually this weekend. So my 3 middle-ish children are all involved in something in our denomination called Bible quizzing. And what they do is there's 4 people on a team, or up to 4 people on a team, all sitting down at the same time, and they're working on certain books of the Bible. This year's Hebrews and 1st and 2nd Peter, and you're sitting on pads that when you jump off of them, your light comes on, but only the first person who jumps. So you've got 2 different teams that are set up. So with my kids, the ones that I was working with was 2 of my daughters and 1 of the other boys from our church. There was 3 students, and there were 4 chairs. Now, normally, what happens is that people are like you guys in class. Like if I told you next time come in and sit wherever you want, you'd probably sit exactly where you're sitting right now, right? You're sort of these like homing pigeons, right? Like you go back to the same place. You do it in church too, don't you? Yeah. So I know where I sit in church, and I know where that person sits, and I know where this person sits. Like it's a known thing. Okay, so this is what happens with these kids when they get in these chairs too. Like they just sit in the same seats. And so the first time they sat in these seats, and then the second time they changed it, and I'm like, what's going on? And the third time they changed it again, and I'm like, Abby, what are you doing? I was like, you're just messing me up because I'm keeping score. So every time they move people around, I have to remember where they're sitting. I mean, like I've got it written down, but it's just not it's not comfortable. It's not what I'm used to, right? They've moved them around. I'm like, they're gonna quiz. They're gonna have 14 different opportunities to sit in these chairs. Okay, 14 different quizzes during the day. And I tell my daughter, I was like, there's not gonna be enough quizzes. There's not gonna be enough of these rounds of quizzing for you to do a different way of sitting every single time. She was like, no, I think there is. And I was like, well, why then? And I knew she was right that there was, but I was wanting to get her to think, because that's what I do, right? And so I was like, well, but why? And she was like, I don't know why, but I just think there's a lot of ways that the three of us can sit in these 4 seats that are different. So she's exactly right, and it was exactly this argument. There are 4 seats. And one of them is going to be empty because I only have 3 kids. Okay, so one will be empty, so that's not going to be, we're going to consider that to be a different seating arrangement. All right, they're going to leave a different seat blank as well as an option. So what happens is that the first person that comes in, there's 4 different people who can sit in seat number 1, which means there's 3 different people who can sit in seat number 2, 2 different people in seat number 3, and then there's one last person or blank spot in seat number 4. And what happens if you multiply this out? Yeah, you actually get the same value that we got over here, which is 24. And so as soon as those words were out of my mouth, I don't think there's enough. I knew there were enough because this is what I was thinking. My daughter felt like there probably should be enough even without knowing there really should be enough. It's the fundamental principle of counting. All right, so it's the number of ways that you can arrange things is what it really is. So let's take a look then at another way of arranging things. These are called permutations. There's 2 different types of permutations, and these can be tricky to distinguish between or to remember the 2 different types. The first one is a permutation of like objects. So there's n elements. Choose R1 of which are alike and R2 of which are alike. Alike objects are indistinguishable. I'll give you an example. Then the number of ways that something like this can happen is n factorial over R1 factorial, R2 factorial, R3 factorial, and so forth. Indistinguishable objects. So this scenario, it can't be people. People are not indistinguishable, right? It has to be objects. So your book likes to do things with flags, running flags up flagpoles. I don't know why. I think candy's so much more fun, so we're going to do candy. So we've got a package of Starburst, and there are 4 red, 5 pink, which are the best flavor, by the way, 3 yellow, and 2 orange in the package. They should just be all pink. They actually make some of them like that now, don't they? Yeah. You don't like pink, Alicia? Are you serious? Oh, man. Next time I buy Starburst, I'm going to give you all the extras left over. Okay. So the thing is that pink Starburst number 1 and pink Starburst number 4 are indistinguishable. They're exactly the same. Agreed? They are. So this is a true example of things that are indistinguishable, not people, but candy works really well. So there are 4 different types of candy. So each of these 4 types is one of these R things in the denominator, right? They are distinguishable. Like the red's distinguishable from the yellow, no doubt. You stick it in your mouth, you're going to know you got the wrong flavor that you wanted, right? Picking them out of the dark, right? You know what I'm talking about. So this is an example of that, and we would have on the bottom each of those different scenarios. So it said that I had 4 red, which is 4 factorial, 5 pink, 5 factorial, 3 yellow, 3 factorial, and 2 orange is 2 factorial. So far, so good? What goes in the numerator? Well, the numerator is all of the Starbursts added together, factorial. So, how many Starbursts do I have? 14. 14 factorial. Okay, everybody good so far? See where all the pieces came from and all of it set up. Awesome. Here's the thing you can't do here. This is not just multiplication, right? It's not 14 is able to cancel with the 2 in the denominator. You can't do that. Because what's going on is in the numerator, you don't just have 14. You have 14 times 13 times 12 times 11 times 10, all the way down to 1. Yeah? So if you were to sort of try to do this, and I have students trying to try to do this, and they say this is 7, no, it's not. You just canceled out a whole bunch of factorials accidentally. So there's no canceling out factorials unless they're identically the same. So one thing we could do is we could write down 14 all the way to 1, 4 down to 1, 5 down to 1, 3 down to 1, 2 down to 1. We could do that. But there's some shortcutting that we can do too. We're going to write down 14 down to 5. So 14, 13, 12, 11, 10, 9, 8, 7, 6, and 5. And I'm going to pause, which was great because I ran out of space. And then I've got the 5 factorial in the denominator, and then I'm going to write the other ones out as well. I'm sorry. Yeah, and then I had a 4, 3. I think I moved the order around. My bad. But there's 4 factorial right there. 3, 2, 1 is my 3 factorial, and 2, 1 is my 2 factorial. I'm just separating so you can see each of the pieces. But the thing is, if they actually match, like identically, not just that you can reduce one by the other, right, like I was trying to do before, 5 factorial is 5, 4, 3, 2, 1 in the numerator and the denominator, and so you can cancel those out completely because they identically match. So that shortcut's writing a sum of this down. 5 factorials go away. And then you can start reducing things as well. So do you see anything you could reduce? Like, for example, here's 4 and 3 and 12. I like that one. Anytime I can cancel 2 things in the denominator with 1 thing in the numerator, I'm happy. Do you see any others that we can cancel?
3, 2, and 6.
Yep, there's a 3, 2 here, and a 6. And all that's left is a couple of 2s. So maybe you do this with 2 and this 2 with this 8. So 8 divided by 4 would be 2. Be really careful when you start canceling things to be right neatly, because you're going to lose stuff if you're not being careful. It's just so easy to lose stuff when you start marking things out, right? So as we're taking a look at this, we have 14, 13, 11, 10, 9, 2, and 7. All of those need to be multiplied together to get my answer. So if you have a color you want to use, like I just did where I sort of highlighted or circled all of them, something to draw your attention to every single term of that. And if you were to multiply that together, what do you get? It's big. Did you get it? Do you want to read me your numbers? Anybody who got it, want me to read me your numbers? Alicia, do you have numbers? What do you have?
2,522,520.
That's what I have too. Ways. This is the number of ways to eat these 14 different starbursts. Crazy, right? Super, super crazy. All right, I think, yes, Kurt.
So I may have stepped away for a split second. Where'd you get the 8 with the 2?
Oh, I just multiplied the 2 2's in the denominator. 2 times 2 in the denominator is 4.
Okay.
And then I reduced that
I was
by
thinking that,
the
and
2.
I was like, 4 to cancel out.
Yep. Yep. Okay, everybody good? All right, this is actually a really nice place to stop before I start talking about the other type of permutation, because the other type of permutation is not like this one at all. It's far more like what comes next, so the grouping of it works better later.